y'all, Darren Lee Berber Jr. back with some more thermodynamics problems. Everything seems to be fine with the volume and everything. Let me know if it's not, if something changes. And I do notice, by the way, what happened to my, well, it'll be all right. That's what I did. Oh my gosh. I made a mistake and what's we call them, locked my background. It's good. Right there. That seems good. I think that one is good. All right. So what I'll do is I'll go through several uh, chapter 4 and chapter 5 type problems and concepts. So I'll try to be under an hour, under an hour and a half. So I plan on going kind of quickly. Probably won't be needing the book much, but I have it there just in case I need to check something out. And the time being, perhaps I'll just put the book cover there. So we'll just do it that way. And if I need the book, then I'll actually load some pages in it. So we'll try that. So these are not problems directly from the book, but they're along the same level of problems. So for the first one, let's go over some concepts. We talked before about processes that are adiabatic and isothermal. So, and I believe I gave the analogy before or the example before that we have a piston and the piston is compressing air. So these are air molecules up in here. And if it is isothermal, we can say that the change in temperature is zero. Like there's no temperature change if it's isothermal. I guess we could take it as iso 1 in thermal. And if it is adiabatic, then we have change in Q equals not zero, if I'm remembering correctly. And here's, I guess, a good reason to pull up the textbook. So what I'll do is put the book covers there. So let us show that like that. So how do we go to adiabatic? Right? So we have adiabatic compression, which is so fast no heat escapes from the gas during the process. So, no, yeah, I mean, that's accurate to say. Change in Q equals zero. So no heat is escaping, so the heat stays the same, so the temperature will change. So if something is adiabatic, I can say change in T equals not zero, change in Q equals not zero. And if something is isothermal, change in Q equals, we don't know. Because looking at this piston here, if we have a flame underneath, if the piston moves out while change in Q is positive, you can have change in T can equal 0. Um, because the piston is going out. At the same time, you can we think if the change in QO, I mean, if it just stays the same, or if there's no energy changing, if there's no flame, change in T can equal 0, and change in Q could equal 0. So uh, uh, that could be out of the way. So if we have a cyclic process, and this goes back to, we're talking about chapter 4 and chapter 5, like we were talking about heat engines before, and refrigerators. But let me see if I could find such a process that has Carnot efficiency. They gave a nice little image of it. I thought it was early in this section. Sometimes they put stuff in the problems. Carnot cycle. This is what I was looking for right here. So if it's a cyclic process where you have P V, and we can see that this is isothermal in the image. This is adiabatic. So I'll call this IA. This is adiabatic, and this is isothermal. We see that the volume is increasing in this part, and the pressure is decreasing. But as the pressure is decreasing, as the volume decreases, so the temperature stays the same because the way it decreases. Here, adiabatic, we have the volume decreasing. No, I'm sorry, hold up. The arrow is going this way. So here the volume is increasing, the pressure is decreasing, adiabatic. So it's such a way where the no energy leaves or exits, and so on and so forth. So the interesting thing about this process is it goes in a cycle. It goes around in a circle. So therefore, we can call this process reversible, because it can go in a circle and it can reverse in the opposite way and still give you the same result. So this is basically for a monatomic gas that this works with. Let me to a different one. So if we have a heat engine, we're just talking about heat engines, and the efficiency of a heat engine is, so basically, if I was to write this out, and let me write both of these, uh, and a refrigerator. So if this is the heat engine and this is the refrigerator, basically you have uh, a hot reservoir, and I'll draw this for both of these. And for an engine, the heat is going into the heat engine, QH, is outputting work. So those who, I'm not sure if I went over this on this channel yet, and heat is dumped into the cold reservoir. So this is basically how your uh, typical power plant works, like what it's doing. I mean, the detail can get pretty complicated, but generally what it's doing is it's taking heat, converting some of that heat as work, and dumping waste heat into the cold reservoir, which is usually the environment, which is why I have the heat stacks there in the image. So making sure it's positioned so you can see those well. Suppose you can see them well enough. Why don't I just move them down some? Okay, so that you can see the tops of them a bit. So basically what's going on is those towers are dumping waste heat from the power plant process of extracting work from the heat energy coming from, I don't know what kind of power plant this is. Let's say it's a nuclear power plant. The heat that's coming from the nuclear fuel is turning the engine, outputting some work that they turn into electricity, and the waste heat is dumped into the atmosphere. Uh, and the difference in heat is what causes these things to work properly. So we have the efficiency, which is going to be the uh, benefit over the cost, which is going to be the work divided by QH. And we can look at the cold engine before we move on. So we still have pretty much the same components. Except in this case, um, we want to dump heat into the hot reservoir like we're heating our home. So we're taking heat from the cold reservoir, like outside, dumping the heat inside, but it takes work to do that. So as you can see, it's just all the arrows are reversed. So for a heat engine, both arrows are going out from the heat reservoir to work in cool, and for a refrigerator, both arrows are going from the cold reservoir to work to the hot. The process is the same. And the well, actually they call this COP for refrigerator. It's still benefit over cost. So that ends up being QH over work. So it's reversed. So if we were to multiply these, and say E times COP, that will be W over QH times QH over W. Now notice this does equal 1. So maybe I should do some more math on this. Let me see here. So I do have the E equals W over QH. Let's scroll for refrigerator. COP equals, that's what it is. Oh my gosh. So maybe I drew this incorrectly. Let's look at the actual image. We have work coming in. We have that. We have QC coming in from the cold reservoir. We have QH going out to the hot. So that is correct. So I guess I would have taken incorrectly. Okay, I got you. So what's going on is let me label this fit cost. So in this case, this is the coal reservoir. We taking coal out of the coal reservoir. So this is the benefit and this is the cost. So work is always included. It just work goes from a benefit to a cost. And on the heat engine, pH and QH is included. On the refrigerator, QH and QC is included. So this will be QC, QC, right? So this equals QC over QH. Okay, so that is more reasonable. And it equals not 1. So a detail to remember here is that for a refrigerator, since we're uh, cooling the cold reservoir, the benefit is the heat that's sucked out of the cold reservoir, which is this. And for a heat engine, the benefit is the work that we use to make electricity or whatever we're doing with it. Let's see here. Why don't we do phase changes? So basically, like let's use water for instance. And let me see if I can remember this from my chemistry class. So why don't we call this axis Q? We'll call this axis T, and we'll call this ice, water, and steam. So the way it works is we add heat to ice at a certain point, even though we continue adding heat, the temperature doesn't go up, and that's the transition state. And it becomes water. At a certain point, we continue adding heat, the temperature doesn't go up. It becomes steam, and it starts getting warm again. So call this ice. We'll call this water. and we'll call this steam. And these are the phase transition states. So at that point, and welcome who is watching, be sure to drop a line. Let me know if you have any questions as well. Make sure you like, subscribe if you haven't already. Help me get to 1,000 subscribers. So basically what's going on is at these positions here, we have a phase transition going on where essentially the heat capacity is zero. Excuse me, is infinity, because we're adding heat, at least for that period of time. You can, and I really don't understand why they say it's infinity, because I mean, eventually you add up enough heat where it changes state, but technically the temperature doesn't change. So they call it a heat capacity of infinity. And there we have it. So we can see phase transition is a change in the state of a substance as its environment changes. Let's see if I can find anything else that might be warranted for a phase transition discussion. All right, let's see here. So this is basically what well, I guess it's similar. This is a bit more complicated one where you can see how there's critical points. I believe the critical point is where I can't tell the difference between water and steam, and the triple point here is where, and I've seen a video of it where you can see a combination of ice, water, and steam in the same area as they're at the perfect pressure and perfect temperature, where it's kind of like all of them at the same time, which I thought was pretty cool. All right, a phase transition transformation. To call this transformation. A phase transformation is a discontinuous change in the properties of a substance as its environment is changed only infinitesimally. Right, so one more time, a phase transformation is a discontinuous change in the properties of a substance as its environment is changed only infinitesimally. So it seems like that's important. I'm looking here. Does the environment change only infinitesimally? Well, I suppose you have to think about that. I mean, if you consider the environment of ice to be the surrounding ice there's a point where there's a transition between ice and water where the temperature doesn't change. So I guess I could see that. All right. Let's get to some problems. All right. So let's say that an engineer has a schematic of a heat engine. Always good to practice drawing those. So we have TH, heat engine, is outputting work and is dumping uh, heat into the coal reservoir. Right. So we have our heat engine here. And let's imagine that the engine extracts heat. And actually, why don't we move to the next one? So we just did heat engine. I feel pretty comfortable with heat engine. Why don't we look at what I hate, which is deriving stuff? So what if we derive the thermodynamic identity for G Gibbs free energy equals U minus PV plus minus TS plus PV. So we have derived the thermodynamic identity for G equals U minus TS plus PV, and then find a Maxwell relation for change in S and change in V. All right. So as I said, I hate proofs. Um, but so I need to practice these things uh, so that I can get better at them. So why don't we do VG equals D U minus TS plus PV, which equals, we know from the law of derivatives, du plus minus dTs plus bPV. I can actually draw this better. du minus dTs plus dPV. So then we have du minus, let's go TdS minus SDT plus TdV plus VdP. Let me know if that's confusing at all. Let me draw this one better. All right, so we have this. Uh, we want to get S by itself and V by itself. Now we can make U equals 0. That'll do it. Um, right? We want S and V by itself. So do I have my formula sheet? I think I do. Yes, I do actually. My newer formula sheet. I don't think I do, but this one will do. I will try to find my newer formula sheet, which I know has a few more formulas on it. But I guess this one will do then. So I do see this one here, du equals T ds minus P dv plus mu dn. And I think what's going on is we could assume, actually, I'll just put the whole thing in there. I'm going to use this. So we have, I'm going to need more room, T ds minus P dv plus mu dn minus T ds minus s dt plus P dv plus v dp. So if I were to uh, move the parentheses, and let us see what cancels. So I have minus pdv plus pdv. We have plus tds minus tds. We want something for changing s and changing v. Okay, maybe I read that wrong. Okay, nope, some kind of change in entropy, some kind of change in volume. Okay, so we can say dg equals mu bn minus s dt plus v dt. So now I have s in v, and let dn equals 0. So the particles are not changing the same amount of particles. So dg equals mu dn equals v dp minus s dt. So if dt equals 0, then dg equals minus s dt, and s, which is entropy, equals negative uh, dg over dt, and this is for a constant pressure and constant uh, particle number. And if dt equals 0, make sure I still need this in terms of, so we want a thermodynamic identity for G, so we keep in G and everything. So if that equals 0, dg equals v dp, and v equals dg over dp, and that is constant temperature and constant number of particles, right? And for my formula sheet, I knocked my mouse down. So we have these two relations. Okay. Let me look up Maxwell relation in the textbook. I have like 15 more minutes. And 158 here. Oh, okay, here we go. So we have S equals negative dg over dt. Okay, good. Got that right. The constant uh, P and N. All right, so that's good. We have V equals dg dp. Good. So yeah, I could have kept the U in there if I wanted to. And said if dt equals 0 and dp equals 0, then gg equals mu dn. So mu equals dg over dn, and constant temperature and pressure. So that's the last one that they have. So I still seem to be missing. Okay, here we go. So here we are here. Functions encountered in physics are generally well enough behaved that their mixed partial derivatives do not depend on which derivative is taken first. Therefore, for instance, partial v partial us equals partial s partial uv, where each partial v is taken with s fixed and each partial s is taken with v fixed, and n is always held fixed. All right. So So this is always held fixed. So this one is a relation, but it's not related here. On the thermodynamic identity for U, you can evaluate the partial derivatives in parentheses to obtain. All right, I'm going to ask Professor about this last step. So I know that these two are part of it. All right, we'll move on to another one. Mm, see what I did with that one, right? Let's do one quick one, then I'll call it a day for now. So we have a system with the multiplicity of the energy equals energy over E naught, where E naught equals a constant and E is the energy. How do I draw this? What do I draw here? What is the Helmholtz free energy of the system? If it is at thermal equilibrium, okay, we want the Helmholtz, which is this equation, F equals U minus TS. And that should be on my formula sheet. Yep. It's Helmholtz free energy. Uh, what is the Helmholtz free energy if it's in thermal equilibrium? We have the properties that is in thermal equilibrium. With the reservoir, as we discussed before, a reservoir is uh, uh, something that's so large that the temperature doesn't change appreciably when energy is added to it. And when it's in thermal equilibrium reservoir, when it has an E equals to E naught. And we want it in terms E naught and A. So this would be easy enough. Uh, so we have F equals U minus TS. And energy is E, which equals U. So we have E minus And we know entropy. Those who have been following along a few videos is K ln times the entropy times the multiplicity. We have T K ln. In this case, it's the multiplicity E. So F equals E minus T K ln E over E naught. And we know that E equals 2 E naught. So we have E minus T K ln 2 E naught over E naught. So that means that F equals energy minus K T ln of 2, where these two things cancel. Yeah. And E is 2 E naught. Want it in terms of E naught and K. All right. So that's just a bunch of substitution. All right. So thanks y'all for watching. I'll go ahead and call it a day and go ask Professor about this one here. There's office hours going on right now. So I'm about to go join the rest of that. And I will be back Saturday on my other channel to give a sort of overview of quantum. So it won't be as in-depth as going problem by problem, but I may come here earlier in the day. Actually, I have a tutoring. I give a tutoring that day, so I may not be here early in that day. I will be here that night on my other channel. But my other channel is more of an overview, so check it out. There'll be an overview of quantum mechanics of uh, putting a subatomic particle in a magnetic field, like an electron or something. So we'll look at that then. Thanks all for watching who are watching. Be sure to drop a comment if you have a question or a comment. Subscribe if you haven't. I'll see you all next time.